So if we break down what's actually happening here, in the slow method, we have H is overwritten by Z transpose HZ, where Z is equal to a product of householder transformations whatever householder transformations you would use to compute the QR factorization of M. Now, in our faster method that only takes order n squared operations per iteration, we're using this matrix, H Z tilde, and Z tilde, as I've described, is a product of other householder transformations. Okay. Now, we went out of our way to make sure that P naught, the first householder transformation, is the one that would be used in the QR factorization of M. So in fact, the first transformations really do agree. So we have that much at least. Now, let's take a look at the other transformations in each case. So these transformations work on columns 2 through n minus 1 to get upper triangular form. These transformations work on columns 1 up to n minus 2 in order to get Hessenberg form. Okay. Now, so these transformations are meant to accomplish very different purposes. Not only that, these household reflections are applied to M, the M that we're not computing. These are working on columns of H. So two sets of household transformations apply to two different matrices to achieve two different objectives. Why on earth should they possibly be the same? So the key factor here is both groups of these transformations only affect rows 2 through n. They don't affect the first row. So that means so they don't affect the first row or column of let's see, actually don't affect the first column of Z or Z tilde, because so they work on the rows 2 through n of either M or H. But now when you're accumulating them on the right to form Z or Z tilde, they don't affect the first column of either of these matrices. So because the first transformations of each are the same, Z and Z tilde have the same first column. Now, we have two transformations applied to the same matrix, Hessenberg matrix H, to produce a new Hessenberg matrix. Both transformations have the same first column. What does that mean? What can we conclude from that? That was covered last time, so we have plenty of time to forget it.
Means they're the same.
Yes.
First column. The
Yes.
first column of
Well,
is unique to the.
yeah. What result is that? That lets us conclude that.
The implicit Q theorem.
Yes, it's the implicit Q theorem. Okay. So Z and Z tilde are essentially equal. So the only difference is certain columns might be negatives of each other. Now we're preserving the eigenvalues in any case, no matter what similar transformation we do. So as far as the matrix H versus H tilde, they're not necessarily the same, but their entries might be, assuming we're dealing with real matrices here, and mostly might differ by a sign. So the thing that's very important is the convergence is going to be exactly the same, because entries of this matrix will go to 0 exactly when they do here. So we've managed to cheat and save ourselves the order of magnitude by appealing to the implicit Q theorem and the uniqueness of Hessenberg reductions. So it's because of this crucial step that we even have an algorithm for computing the eigenvalues of a general square matrix. I don't want to erase that other stuff yet. So if we go back over here momentarily, describe this process. It is called a Francis QR step. So this is how the double implicit shift method is used in a practical setting to try to reduce your Hessenberg matrix H to upper triangular form as quickly as possible. So John Francis, around like 1960 or 61, who came up with this. He was not in academia. I forget, I don't know what company he was working for, but so he published this, and then he left numerical analysis altogether and had no idea that he was revered in this field until my advisor, Gene Bell, tracked him down in 2007 and let him know that, hey, you're famous. And so he appeared at some conferences, so now he knows. I think he's passed away since then. I'm not sure, but at least he got to know what an impact he had. Okay, so now as far as completing the method, again for efficiency's sake. All right, actually, yeah. Now I can go ahead and erase this stuff that you already have in your notes. Well, what's interesting is I believe someone else in, I think in Russia, came up with a similar approach, like, independently of Francis. But you don't hear from getting credit for it. I can't even tell you her name. And maybe that's because Russian names are often difficult. But it wasn't just Francis who did this.